Morning, everyone. So first thing this morning, we have Steve Capper from ARM talking about PAC and BTI and Debian. What are they and why should we care?
Yeah. Thanks, Sissy. So hi, guys. Yeah, I'm based at ARM. I'm the tech lead for the distributions team. And one of the distributions we like to look after is Debian. So there's a few of us here for the Debian mini-conf. We're deploying architectural features for hygiene and security more than anything in the architecture. And I thought rather than have a sort of reference guide or something, we could actually just talk about one of the notable security features that's coming quite soon, and indeed already is in quite a lot of hardware already, and explain how we're putting it into Debian, and also explain what to do if there's a problem, how to debug, essentially. So this should act hopefully as a reference for future as well. So I'll introduce some architecture to begin with, and then I'll go through how we're actually applying that in real life to the distro. So let's start with Pointer Authentication and BTI. So don't worry too much about the assembler. I'll describe what the issue is. So we now have a degree of security where the stack is not executable, the code segments are not executable. However, that does not prevent somebody from changing the code flow of a program, because one avenue of attack that has been neglected is the so-called return address, which I've highlighted in bold here. So the idea is, rather than overflow the stack with code, you overflow the stack with a return address that already exists somewhere else in text already. And you can actually, disturbingly, one can form a Turing-complete attack using fragments of libc, and the colloquial expression for this, you hear the security people call them gadgets, which is basically just code that we already have, but used in a different way, just by modifying the control flow of the program. And so we've got a thing called Return-Oriented Programming Style Attack, or a ROP attack. And so what would happen here is, in bold, X30 would be set, it was also known as the link registers, the return address in ARM. That would be set to something it shouldn't be, and execution will continue in a code path that it should not be in. So this is how we try and solve return-oriented programming style attacks. So we've got something called Pointer Authentication. So what we do is we have a series of secret keys per process that the kernel manages, all transparent mostly to user space. And what we do, user space can take the return address pointer and sign it. Now, a traditional pointer in ARM will go up to about 48 bits of virtual address space. We've got some space here, and so what we do is the signing instruction will throw some extra data in here as a signature. So the idea is, when you want to use the link register again afterwards, you check the signature, authenticate it against the rest of the pointer. If the authentication passes, you get a pointer that works. If the authentication fails, you get absolute gibberish in the entire pointer and an immediate translation fault or program crash. I'll go through that in more detail. So the idea is that the return addresses are stored and basically signed and authenticated. And that's the idea, to try and stop, let's say, X30 being corrupted, because it would be detected. So it's all well and good saying this. So how do we do this? So what we do is we have some extra instructions in ARM. I won't go through a list of instructions. They are documented, and the compiler understands this. So in this program, what we have is, as I alluded to before, we have the signing instruction and the authentication instruction. And if this authentication fails, this return statement will just go haywire and everything will crash in hopefully quite close to where the attack happened. Now, the really clever thing about this is that these so-called extra instructions are actually in what we colloquially refer to as the NOP space in ARM, which means if you've got an old CPU, it goes and goes, oh, I don't know what that means. Rather than have an error or, a legal instruction, it's a NOP. So what we can do is we can retrofit these into user space quite safely, and it will just execute on old hardware as if nothing ever happened. And so what we do to get these instructions is the compiler, GCC or Clang, and some others as well, you pass a special flag that says branch protection equals standard, and that will put this in for you into user space. So that's why we're trying to push this into the, I think, depackaged dev package to try and put that into the build flags for the Debian system. Now, I've mentioned that we've protected against return-oriented programming style attacks, and that's basically where we get return from a function and we authenticate. Unfortunately, I think shortly after this PAC was done, there was another style of attack called a jump-oriented programming style attack. So it's very similar to a ROP attack. So rather than corrupt the return address, which is what a return-oriented programming style attack does, instead you target pointers stored in structures. So, for example, a virtual function or something like that. So if you can corrupt that, then you can branch. You just jump. In ARM we say BR, but other instructions like jump or whatever in similar architectures. So the idea is we can corrupt other things for jumps instead of returns, and we get the same thing. We get the gadgets, we get the execution of an attack. And so we've got an architectural feature called Branch Target Identifiers, and this complements PAC. They come in pairs. And so we have this thing called BTI. Again, what we do with BTI is a slightly different strategy. So with a return address is usually stored locally within the stack frame of a function, so it's kind of self-contained, and it's quite easy to try and sign it and authenticate it. With a random branch to somewhere, God knows where it comes from, it could be anywhere, it's not easy to place boundaries on and persist and authenticate. So we've got a slightly different strategy for BTI. So with BTI, what we say is these are the places you are allowed to jump to. If you jump anywhere else, kaboom, you're not allowed to. So that, in theory, stops the gadgets, because you can only jump to bona fide entry points in functions or where you should be going. And this is called prop BTI. And again, this command line flag will be familiar because I've just introduced it for PAC. This command line flag that we're trying to put in does both PAC and BTI for free. And the BTI instructions, again, they're in the NOP space. And you can also, there's some special stuff in the architecture to minimize the number of instructions. PAC instructions can also count as places to jump to as well. So I'll just show this in a picture because it's easier. Right? So here's an example of BTI. So I've got my amazing C program on the left-hand side. And what I've done is compiled it with branch protection equals standard. So I've got some assembler on the right-hand side. I'm in my main function here. And my standard branch and link, so on ARM speak, that's just jump to a function and expect a return. Jump to X1, I can land here, but if I was to land here, it'd go kaboom. So the BTI says, you can land on this if you're a branch with link. In other words, this is a call to a subroutine, you're allowed to land here. And so this will stop, in theory, the job style attacks. And again, this is all done for us by the compiler. So we're trying to introduce this quite aggressively because the actual risk to the system is quite low. I'll talk about some extra sort of information on how to deploy these as well. I should stress that for most programs and most software, I don't think people need to do anything. So I'm going to cover the awkward bits. And there are a few, but it should not. Out of all the software we've tried, it's been quite limited where there have been awkward bits. So just to recap, the PAC instructions are implemented in the prologues and epilogues of functions. In other words, the beginning and end of a function that the compiler emits. Most of the time, it's done for us. So, however, there's one exception where we have to think about this from a software point of view. If one is writing a debugger that unwinds the call stack, it would be nice to actually unwind it properly. We've already got, there's a special instruction to do this dead quickly that just strips everything off and leaves a pointer. We've already got this in libunwind and friends already, but if anyone's doing amazing JIT or amazing runtime and they want to use PAC, then they need to worry about the unwinder. Kernel toolchain all have PAC support as well. So that's all in there upstream. It's been upstream for years, actually, I think, as well. So all the bits are there for PAC, basically. BTI gets a bit more complicated. As I mentioned, there's these landing pad things. Now, most of the time, if most of us here are quite easygoing, simple folks who like to write stuff in high-level language, maximum portability, recompile, go to pub. There are cases where people still use assembler for some reasons. There are times where assembler is needed. This is where it gets slightly trickier with BTI. Now, the good news with BTI is, let's say half the program's compiled with BTI awareness and half the program's not compiled with BTI awareness. The runtime, the linker will basically say, not everything in this program knows about BTI, so I'll play it safe and I'll disable BTI. So for stuff that does not fully port it over with BTI, there should not be a problem. So there won't be any crashes or anything. It just won't switch on. And I'll go through how to see if it's switched on in a sec. So, but basically, the other thing as well is the way BTI works is all the code's got to be BTI aware, which from a Debian point of view, this is the applicable bit, the Debian point of view, the prerequisite libraries of your program need to be BTI aware. So that's I'll mention a whoopsie that I overlooked and just found out before the talk, and so I can show you how we debugged it. But from the Debian point of view, the takeaway for this is we need a lot of the prerequisite libraries to have BTI support. In other words, we want as much of the AH64 or ARM64, distro to be compiled with branch protection equals standard as possible. And that way, it's easier for this stuff to switch on. Now, assembler, don't worry too much about this. This is for reference. It's not enough if someone's got an assembler file to just put BTI instructions in. You have to put a special ELF note section in, and that tells the linker that I know about BTI. So this is for reference. This is how to do it. The good news is most people here will never have to touch assembler, and that's the right way of doing it. But if one is doing assembler, they'll need a note section. But it's documented here as well. But, and the BTI instruction itself can be found documented in more detail as well. But I do not expect people here to be writing assembler or BTI instructions. Hopefully the toolchain does all that for you. Okay, so that's a whirlwind intro to the architecture and it's how it's deployed. Now I'm going to say what happens when stuff breaks. So this will be useful as a reference, but the good news is I don't expect much stuff to break. We've been running this quite a lot, and it's not been a case of earth-shattering kaboom when we switched it on. So, but it can happen. So PAC and BTI, their security features, they could be tripped. Security features get caught if something goes wrong. I've written on this slide an attack mode from each side, but an attack mode could be malice or more likely incompetence. It's probably incompetence somewhere in source code doing something it shouldn't. So I'll go through PAC. I've described this, but this is a nice little summary. If the return address is corrupted, the authenticate instruction will fail, we'll branch somewhere we shouldn't, translation fault, seg fault immediately. So if you're dealing with PAC and you see seg faults where you don't expect to see them, and your program counter address is crazy weird, it's probably an authenticate instruction gone wrong. Now, with BTI, again, the attack mode is the function pointer gets corrupted, and you jump somewhere that you shouldn't. So you're jumping, you're not landing on a landing pad anymore. Now, what will happen is, in the ARM architecture, we have this thing called the branch target exception, and that's because the kernel's told the CPU that BTI should be enabled with a guarded page. What we see as the end user is we'll basically see a SIGIL. So if you see a SIGIL, and you look at, and it's an illegal opcode, and the instruction looks like a bona fide instruction, chances are it probably is a BTI crash. Now, there's a slightly easier way to debug this as well. We have the kernel kill switches. So these are very useful. If we do suspect there's a PAC and BTI or BTI issue, rather than spend a lot of time debugging, we can just switch them off. And so there's kernel command line flags which deactivate them hard. So if I pass ARM64 no pauth or ARM64 no BTI in the kernel command line, that will just stop the kernel from using it. It will stop it being advertised in user space. And if those instructions execute, they will be NOPs again. So in other words, we go back to factory settings. So if there's an expected issue with PAC and BTI, the easiest thing to do is switch them off and then test. And then more fine-grained debugging could happen from there. So the common issue we're having, this is more for myself, Emanuela, and Wookie to worry about more than you guys, but we're trying to deploy BTI across the software and the archive. If, as I said, it's advertised whether or not a piece of software supports BTI in the ELF file. There's the read elf-n, that'll tell you if BTI is enabled. So it'll tell you if it should be on or not. If BTI is listed, BTI is not listed, the runtime loader just won't switch it on. So that's a good test to see if it's there. Now, I just was confidently going to show an example in Sid showing BTI enabled, and then no, it wasn't enabled. We made a mistake. So, okay, so we get to a situation where BTI is not enabled. How on earth do I figure out why? And this is, again, don't worry too much about the output. This is the key thing here. There's a magic flag that you can pass to the linker that says, try and force it on and give me a good telling off if you can't, and tell me why you can't switch it on. So we found, for example, this is an old, I think this is Bookworm, but for instance, if I try and force BTI on in Bookworm, the actual GCC runtime doesn't have BTI enabled. Because the GCC runtime doesn't have BTI enabled, the resultant program will not have BTI enabled. So this is a very quick way to say, how on earth do I switch this on? And that will tell you. If you use this flag, do not put this in dpackage dev, please, 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 because the binaries will crash. It's telling you that it's wrong. Just use this internally and then fix it and rinse and repeat. So the status with Debian is we've got the flag enabled. I think it's for the hardening flags. We've just realized that we need it in other places. We're following up. So if you see a weird email from a friendly ARM colleague about branch protection equals standard, you'll know why. We're just trying to switch it on. Yeah, now this would be a good place to stop a talk, and it'd be sensible. However, let's do some bonus architecture, because people aren't side enough and haven't been quick enough. So I'm just going to give, yep, hello? Yeah. Yeah. Yeah.
Thank you very much. For PAC and BTI, how does it work? It's a syscall that is being completed by the kernel, or the CPU is
it's activated by different mechanisms. So the BTI is an mmap syscall that says, please enable BTI on the following memory pages. The runtime loader will do this automatically for you, so don't worry too much about it. If you do an strace on a program load, you'll see a sneaky flag being added to the mmap as it remaps for BTI support enabled. PAC, I think it's mostly done in the kernel automatically. You've got the secret keys per process, and you do have a process control interface, a PRCTL, so you can do clever things with the keys, but I don't think you need to. I think it will just work.
But does that mean that for every instruction now we are going to have two syscalls?
There's no, the instruction's executed by the CPU.
Okay.
Yeah, nothing traps. It only traps if stuff goes wrong, and that's when it's crashing or there's an error. That's when it, yeah, don't worry, it's not a syscall in every function. We're not that heartless. No, it's fine. Yeah. So, okay. Any more PAC BTI before? Oh, yeah.
So, as I understand it, for BTI, there's an instruction on virtual functions that you can jump to, right?
That's an example I made up, but yeah, you've got function pointers you can jump to, and those can be corrupted.
So I guess that protects against jumping to any random code?
Yes.
But it doesn't protect against jumping to a random function that you shouldn't jump to?
Yeah, you're right. There's a slight bit of protection. I'll show you here. But I agree with you. So you got this BTI-C here. So this means it can only be a branch and link. You can just have a normal indirect branch as well, so it does make the distinction between the top of a function and the middle of the function at least to try and mitigate that a bit.
Yeah.
Yeah.
Do you have an idea for how to protect against jumping against a different function where you could maybe corrupt the stack?
I do. It's in the bonus architecture.
Okay.
Yeah.
Thank you.
Hey, Andy.
Okay, just staying with BTI,
Yeah.
you mentioned that the entire platform needs to support this, which means all the libraries need to support this.
Yes, yeah.
So we've now got a brand new attack vector because we've now got a nice piece of code which
Yeah.
is using a shared library,
Yeah.
and we now have introduce a shared library with BTI turned off, and therefore the rest of the system silently fails
Yeah.
for the protection.
Yeah.
So as the end user, you don't necessarily know whether BTI is working on your.
Yeah.
I need it to work.
One thing I was flirting with would maybe, again, the Debian packaging guys, you guys can throw stuff at me, but it kind of feels almost like a Lintian rule where it could just check the notes. But I need to think more about it. But yes, exactly. But I don't know how to solve it yet. I'm happy for the community to work with us, and we can figure it out. Oh, sorry, Dan. Yeah.
Yep.
Yeah.
You mentioned that the entire process has to be BTI enabled.
I think it's... Okay, this is complicated. So, for when you're linking, all the execution units that form an executable have to be enabled. I think it's fine if you're traversing shared objects at runtime because you've got the protection mapped in with the kernel. So that should be fine.
So would it theoretically be possible for a BTI-enabled process to use a non-BTI-enabled shared object?
Yes. So what you can do is if you look in proc SMAP, so proc PID SMAPs, so maps gives you the normal mappings, but SMAPs gives you the flags. You can see that there's executable, and you can see some of the mappings are BT, which means they're BTI enabled. So the way to think about it is in terms of the VMAs, like this VMA is BTI aware. But in terms of what we do for the software compiling, because we don't know if it's assembler or whatever, we play it safe with the compiling and linking, but it should interoperate with shared objects fine, because you could just DL open something mid-flow, then the toolchain doesn't know about that at compile time, so it's done per VMA.
And if we were to get to the sort of the ideal world where everything has been compiled with BTI,
Yeah.
will there be a way to tell the kernel you may not map something executable except if it is mapped BTI enabled?
It's tricky because the way the loading sequence works, it would be possible to certainly add logic around to figure this out. The exact mechanics of how it's done, because the runtime loader basically, the kernel will basically load the runtime loader, and I think the kernel will actually map the runtime loader with BTI enabled, but I need to double check, I don't know for certain. The runtime loader will mmap all the executables, and then it jumps to like an AArch64 section, which then says, I will do the BTI fix-up. So it kind of, you see an mmap once and then an mmap again. So it's certainly doable to basically enumerate everything that's running and say, you've got a security problem here. That's probably the easiest way to do it, to sort of just have a monitor that just goes and checks all the executable things and says, that one's not BTI, flag, flag, flag to the user. But you could do that now with a bash script even.
So I'm thinking about this from the perspective of safety systems.
Oh, yeah.
Where
yeah.
you might want to be able to say,
Yeah.
this system cannot run code that does not have these mitigations in place.
Yeah, potentially you could. I just don't know enough, sorry, about the process startup. Potentially, yeah.
Thank
But
you.
Mark knows. Yeah, sorry, were you waving for 10 minutes, Mark? Do you want to give him a microphone? Yeah. Yeah.
I'm implementing the kernel support, so just to answer Daniel's Daniel's question. We don't currently have a plan to do that. That is a useful idea. At the minute, the protection is per page, as Steve said. At the minute, the process is that the kernel starts the dynamic linker with BTI protection enabled, and then the dynamic linker is responsible for anything that happens after that. We could add something that doesn't actually implement execute no BTI permissions, but we have not done that, so that capability isn't available to user space. It would need to be done with the cooperation of user space.
But I think the least intrusive thing, I think, would be to diagnose rather than enforce process startup, because process startup's a bit icky, and then once you got past process, but I know what you mean, you want it fully secure. Sorry, I think, were you waving in for a microphone? Oh, no, sorry, yeah.
Thanks for putting some context to the build failures I've seen lately. I wish.
Sorry about that.
So, I do some cross-building, and these flags happen to apply to cross-builds, and Debian has been quite bad at distinguishing build architecture flags from host architecture flags. Unfortunately, an AMD64 GCC is not particularly happy about this new flag and simply fails. So in introducing this, we have to be a bit more careful about how we separate build architecture compiler flags from host architecture compiler flags. And I wish that you all do that.
Yeah, no, thank you. Please grab myself, Ema, Wookie, if we can help. If we've broken anything, we can apologise as well. So... Ian,
so you've answered a bit of this already, but I'm interested in cross-compiler executables that are made by a collection of different compilers, some of which may or may not support this.
Yeah.
So as I understand it, what matters for the BTI is whether the target page has BTI enabled.
Yes.
And that means that you can jump freely to anywhere in pages that were compiled by a compiler without BTI support.
Yes, but if one does a link, the resultant executable will have it disabled. So you're basically talking about libraries at this point jumping.
Right.
Yeah.
Right. So it's on a whole shared library basis, not on...
Yeah, that's the way to think about it at runtime, because compile time is extremely conservative because the toolchain doesn't understand, is this even in the same address space? Is it going to be moved about? So it's very hyper-conservative on that.
Okay. Now, I don't know... So I've been doing a lot of work in Rust.
Oh, yeah.
Do you know what the situation is in Rust?
I'm sat next to a Rust guy. They're looking. They're interested. I don't think there's anything formally done yet. It's being analysed, basically. So, I mean, Rust generally uses LLVM for compilation. Yeah, Clang supports PAC and BTI. The Rust guys have reviewed my slides, so they know about this.
Right, okay. So the answer to that question is...
It's on the radar,
it's not
but we
there
don't know
yet,
official.
and currently, if you make a program or a library, let's say an ELF executable that contains a mixture of C code and Rust, you don't get any of this, is that right?
You'll basically, at link time, it'll do the most conservative thing. It'll do the intersection of the notes and then say, if you're linking with Rust, it's that way. I need to sit down and think about process startup. So, for example, you could have a Rust executable that dynamically loads something that's BTI enabled. I can't remember off the top of my head if the Rust uses the normal dynamic loader. It probably does, which probably...
It does unless you compile your executable weirdly.
Yeah.
Okay, great. Thank you. Well, not great. I mean, we need to work on that. There's a lot of people now rewriting bits of their software in Rust. And you don't want to, basically disable this new feature for protecting C from stupid C.
Yeah.
Just because you tried to write some of it not in stupid C. That's kind of going backwards.
But, no, exactly. But to be fair, I think... the cool thing is, as it stands, there's a Rust crate I really don't like. It's one of the most popular SSL crates, and what it does is it dynamically links to libopenSSL, so you've got the security of C. Never mind. But in that particular use case, the OpenSSL library would be BTI protected, so it would be protecting the Rust process, if that makes any sense.
Right. I'm just thinking about, there's RSVG, there's Endless...
Oh, yeah, there's tons of stuff that'll keep us busy, so we're happy to be busy. We'll keep cranking the handle.
Good.
Other languages are looking as well. We're just evaluating for each thing. This makes a lot of sense for C as it stands, so we're switching it on immediately now. Well, I think I've got time for some bonus architecture. Okay. So... it's just been mentioned that, yes, we could do different functions and they could still have landing pads on. So we have this thing called guarded control stack. So it's documented quite nicely on the ARM website, and there's a link here, and I'll put the link in the reference. So the idea is what we do is we sort of protect the call stack more formally. It's duplicated and protected with a series of architecture and kernel enhancements. And the idea is you your control stack is kind of somewhere else, sort of, and it can only be manipulated by certain mechanisms to try and limit the possibility of corrupting the call stack. It has quite a nice advantage that you get all the call stack in one place. It's really nice for profilers because you don't need to unwind. You can just see it, like, there it is, I know the call flow. So you kind of get the security and a bit of perf profiling for free. This is a very new architectural architectural extension, sorry. I don't even think it's in the ARM yet. It's public, it's documented in the ARM website. So this is just, for the folks here at Debian, there is actually one thing we're interested in. So for GCS, GCC dynamic linker, I think, is still being developed. We do have a kernel thread for Mark on enabling GCS, and I think we've got one issue to think about. And the question for you guys, we don't need an answer today, is if anyone cares about the x86 shadow stack implementation, likes it or dislikes it, either one's good, could they let us know, or Mark know in particular, or myself, because we're probably, if everything's okay, going to follow a similar sort of user space mechanism for GCS as for shadow stacks. But we don't need to resolve this in 5 minutes, but just come to us later, see the stuff on the mailing list. There's some discussion happening. This won't be in Debian for ages, but it's at the sort of early development stage where people that do care about this is the time to influence it. So I've got some references, and I was going to say thanks for your attention. This would be a very sensible place to finish a talk. However, so I've got everyone in a room. I'm going to lock the windows and doors and sell you a timeshare. So the idea is, ARM is a nice company. I've been here for a while. They don't beat me as much anymore. We are recruiting software engineers in sunny Manchester and in Cambridge, and indeed in other offices around the world, for open source software development. We don't have anything in the distros team just yet, sorry. I think for the previous Debian one, I just advertised on Debian Jobs last time. But we do have open source software. We would love, if anyone here is interested, or probably knows anyone who's interested, grab me. Please feel free to grab me direct. The careers website's got a bit of character, so feel free to talk to me. If you're interested or if someone else is interested, let them know, because it'd be nice. And sorry, that's my gratuitous spam done, and I'm happy to invite any more questions. Hey, microphone this way, please.
Thank you again.
Hey.
As far as I understand, the guarded control stack feature is something that is also heading for AMD64. Do you have information about how compatible these are?
I'll just be honest and say I do not know. Do you know, Mark? Is it worth microphoning you?
I don't know anything about the AMD 64 specific implementation, or the AMD implementation. The Intel implementation is not quite software compatible because, but at a very low level in terms of almost everything using it. It's the flow is basically the same. So if you can work with, unless there's some massive change in review, if you can work with the x86-64 shadow stack feature, it's called, then you will work with guarded control stacks. It's the differences are very low level toolchain and libc sort of stuff.
Okay. Anything else, guys? One thing I was going to say is a particularly nice reference is, I think Mark sent me this. I've said it's nice on the slide, and it's really nice. It's actually well written about ROP and JOP style attacks and isn't blundered on like I have been. So that's a very nice, succinct way of doing it. But these slides are on the wiki, so feel free. Okay. I think we're good. Are we good? No. Mr. Wookie.
Slightly tangential, but we turned on stack clash protection at the same time as this stuff in Debian, and it turns out that on ARM32 some things are breaking. The Ubuntu people have got a little bit Maybe told us you're going to turn this on. We're just about to release, and some of our libraries broke. So we're just deciding whether, in fact, we need to turn it off again and see. Mostly Valgrind gets upset because it accesses... The implementation is different on 32-bit from 64, apparently. The toolchain people told us it would be fine, and we believe them. So anyway, basically, just a little warning that that's now turned on everywhere, and it may cause issues on ARMHF or ARMEL. So actually, we didn't turn it on ARMEL, it's only ARMHF. So just a little warning that we may see some issues. Please come to me, I guess, probably, if you do.
Thanks,
we'll see what's going on. It's possible it's only Valgrind, and that's being used in tests, and that's breaking in various places, in which case it's fine. It accesses 1 byte below the stack, and apparently we've just changed the spec to say that's okay, but we need to tell Valgrind. Nobody did. Okay.
Cool. So, guys, I'll let you coffee up. Thanks.